using mode 2, mode 0, mode 1 to generate delay, to generate square wave. Square wave of 50% duty cycle, 40% duty cycle, right? And that is where we end up with the timers. So today we will go with serial communication, right? We will begin with serial communication, right? Now 8051 microcontroller, it has UART type of serial communication, right? UART stands for Universal Asynchronous Reception and Transmission, right? So when we talk about serial communication, right? When we talk about communication, the first communication is sending data from one device to another device. So what are the ways the data can be sent? It can be parallel communication, it can be serial communication. In case of parallel communication, when I say we are transmitting 8-bit data and it is a parallel communication, that means all 8 bits are sent from one device to another device at the same time. And to transmit 8 data, we need to have 8 wired connections. The transmitter and the receiver should have 8 wired connections so that 8-bit data can be transmitted at a time. That is called parallel communication. Whereas in case of serial communication, I am sending 8-bit data, but then 1 bit will be sent at a time. So I need only one wired connection to send 8-bit data because the data is sent one at a time. Is that okay? So that is serial communication. Mostly in digital circuits, we follow serial communication, right? Why? Because the hardware is less. Lesser the hardware, more the reliability, lesser is the cost, right? When do we go for parallel communication? On a PCB, whenever you are communicating data from one device to another device, and both the devices are on a single PCB, on a single motherboard, then we go for parallel communication. But there is a separate PCB and you are transmitting data to another separate PCB, right? So from one hardware to another hardware, then it is preferred serial communication, right? Again, less hardware, less cost. Is that okay? So that is why serial communication is important, right? Nowadays, you all have sensors, right? See, various sensors. Those sensors sense the data, convert it into digital. There is a sensor module which will convert it into digital because there is ADC on that module. And the digital data is transferred to microcontroller serially. Okay, so you have nowadays those sensor modules are available which perform serial communication. Even memory data transfer is also many of the times serial communication. Okay, now 8051 microcontroller, right? It has one serial peripheral circuitry. And what type of communication it is? Asynchronous, right? So we saw the initial category of communication is serial and parallel. We prefer serial communication, and under serial communication, again I can have two varieties: synchronous data transfer and asynchronous data transfer, right? So mostly again in those two, the preferred one is asynchronous, right? Asynchronous mean the operating frequencies of the two devices can be different. Whenever we transmit data one device to another device, it is not that always both the devices will be operating at the same frequency. Right? If it operates at the same frequency, we prefer synchronous communication. But microcontroller is operating at 12 megahertz, and the other device, suppose printer is operating at some different frequency. Correct? In that case, asynchronous data transmission is preferred. Correct? Now, UART stands for Universal Asynchronous Reception and Transmission. We are going to see what is this UART meant. Okay. Now, again it is, in case of 8051 microcontroller, how is the serial communication? Full duplex. There are three categories, right? Simplex, half duplex, and full duplex. Simplex means there is only one way communication, like a television. It will always show the video transmit the sound, transmit the video. Okay. So simplex, the device will perform communication in only one direction. Either it will keep on transmitting all the time, or it will keep on receiving all the time. That is called simplex. Half duplex communication is with initialization, the device will start receiving the data, and we change the initialization, the device will start transmitting the data. One at a time. Is that okay? So that is called half duplex. Is that okay? And like your walkie-talkie, right? Walkie-talkie time only that person will be either talking or the person will be either listening. So that walkie-talkie is half duplex. And full duplex is a telephone. I can speak on the telephone, at the same time I can listen also what the other person is saying. So transmission and reception is happening at the same time. That is called full duplex. Our telephone is of that category. So 8051 gives you full duplex UART serial communication. That is, transmission and reception happens at the same time. Transmission happens on TXD pin. Reception happens on RXD pin. That is, P3.1 is for TXD, P3.0 is for RXD. Is that okay? So in 8051, again I repeat, it provides one serial peripheral circuitry which performs full duplex UART serial communication. Is that okay? Now we will see what is that UART serial communication. Universal asynchronous reception and transmission. So whenever we say asynchronous, it means the sender and the receiver are operating at different frequencies. But even though the data which is transmitted is received correctly, right? The transmitted data is received correctly. So that different operating frequency, hence the name asynchronous, right? But then how is that the transmitter and the receiver manage to transmit data and receive data correctly? It is with the help of a frame. Whatever data we want to send, right? Suppose we are sending an 8-bit data. Whatever diagram you see here, right? That is one frame of UART communication. And the name universal is anyone in the world will follow this frame format. Hence the name universal. So whenever the data is to be sent and we are saying we are performing UART serial communication, the data has to be packed in this format. Is that okay? And that is called as one frame. And the data is sent according to this frame format. So this is what is asynchronous transmission, universal frame format. Okay, so let us see what is this format. We are sending 8 data bits. So see here, I am moving the pointer, right? So these are those 8 data bits, right? What are we sending? We are sending character A, right? So during transmission, we say it is a character. What do we send? We send its ASCII code. See, whenever the characters are sent, we had seen that LCD program. Whenever I want to display some character, either I put it in quotes in the program, but these hardware circuits are digital circuits. That character A automatically is converted into its ASCII code by the microcontroller. And for example, here the character A ASCII code is 41 hex. Is that okay? So these are those 8 data bits which I want to send, 41 hex, 41 hex. So these 8 data bits are packed in one start bit and 1 or 1.5 stop bit. So at the beginning, there is a start bit, and that start bit is logic 0. Right? So you will have one start bit, and then it's the D0 bit. D0, D1, D2, D3, D4, so on, D7. This is where your 8 data bits end. Right? Then you have you add a parity bit. Again, this adding parity is optional. Okay, you add it or you do not. This is optional, but there should be 8 data bits, and then at the end there should be a stop bit. So stop bit is indicated by logic 1. Start bit is indicated by logic 0. Now from the name itself, this start bit and the stop bit is an indication to the receiver. As soon as they get the receiver start bit, the receiver understands immediately next it is going to receive the data. It is going to receive 8-bit data one after the other. Right? And what is first received? The LSB. D0 bit is a bit received first. Then automatically arrives D1 bit, D2 bit, and so on. And the data bits, what am I sending here? 4, 1. So the sending begins from LSB. So start bit is an indicator to the receiver. The data bits will be arriving immediately next. And when the stop bit arrives, it is an indicator to the receiver that the data frame has finished. So stop bit is logic 1. Stop bit can be either of 1 bit or it can be of 1.5 bit. Is that okay? So this is a frame format. So whosoever is performing UART communication, the data should be packed in this particular frame format. Correct? So if we put the parity bit, again it is even parity, odd parity, we decide. So here it is mentioned even parity. Right? So 4, 1 mean there are 2 logic 1s, mean the parity bit is 0. Again, hope you all remember why do we insert parity? So as to check whether the received and the transmitted data are correct or not. Error detection. Is that okay? For that purpose, the parity bit is inserted. But again, that is an optional. Right? So if we insert the parity bit, the frame, look into what is the frame size. 1 start bit, 8 data bits, then the parity. So 8 plus 1, 9, 10, 11. So if we put the parity bit, one frame is of 11 bits. If we discard the parity, then one frame is of 10 bits. So the data to be transmitted should be clubbed between the start and the stop. Is that okay? And now, where is this transmission and reception happening? It is on those TXD and RXD pins of microcontroller. Okay, start bit logic 0, then D0 bit, D1 bit. So one after the other, these bits will be transmitted on the TXD pin. And if receiver is also another microcontroller, the reception will happen on the RXD pin. Is that okay? And now, if nothing is getting transmitted on the on those TXD, RXD pins, mean it's idle. No transmission is going on. So idle state means always logic 1 appears on the transmission and the reception. Right? So if nothing is getting transmitted, what appears on TX-RX? That will be always logic 1. And if transmission begins, hence that start bit is logic 0. So there should be an indication that the transmission is getting started. That's the reason the start bit is kept as logic 0. Idle condition, that pins will always have logic 1. Hope you get me, students. So this is the frame format which is prepared and transmitted when we are performing UART communication. Okay, now see, find the frame is prepared. That 8 data bits along with the start and stop bit is prepared, and we will be sending it one after the other. Right? So transmitter will prepare this frame format and will first send the start bit, then send the D0, then send D1, and so on. But what happens at the receiver side? So see here, this is that start bit which is logic 0. Then we have shown something like this, that D0, D1, D2, that's some box shown. Right? See, when I am sending a specific number 4, 1, then I know D0 bit is 1, D1 bit is 0, D2 bit is 0. But then the diagram which is shown down is a general diagram. That D0 is shown in one box, some rectangular box, right? That indicates it can be anything. It can be logic 0, logic 1. Then there is that crossover. Mean the D0 bit is getting ended and D1 bit is getting started. And D1 can be logic 0, logic 1. So that's a way to show the data bits in a general format. Crossover mean D0 is changing and another D1 bit is appearing. Again the crossover, D2 bit is appearing. Right? Whereas the start bit is always logic 0. So that logic 0 is shown definite, fixed logic 0. Stop bit is logic 1. So that is also shown as logic 1. But data can be anything. So this is how that transmitter will keep on transmitting. Whereas look at the downside, right? See that dotted arrows? It is at those arrows where the receiver samples that particular bit. Mean at the middle of the start bit, receiver takes in the start bit. At the middle of D0, receiver accepts that bit. So the sampling happens at the middle of that particular bit. D0 bit, D1 bit, right? So this dotted arrows is where the receiver samples whatever is arriving on RxD pin. Right? And the first diagram is how the transmitter transmits the data. Fine. So that is how the reception, even though the two devices, the receiver and the transmitter, are operating at different frequencies, right? With the help of this frame format and with the help of the baud rate setting, both the transmitter and receiver operate such that the transmission and the reception happens correctly. Hope this is understood, students, right? And one more, in serial communication, logic 1 is also called as mark bit. Few technical names have been given. Right? So logic 1 is called as mark bit and logic 0 is called as a space bit. Just some technical names too. Okay, so that's how UART, this is the UART frame format. And that's a technique for transmitting and receiving the data. Fine. Universal mean everyone in the world is going to follow this frame format, follow this transmission reception technique. Okay. Now, so in 8051 microcontroller, right? Now let us see what all special function registers are associated with serial communication. Okay. So the one is SCON, serial control register. From the name itself, this is going to control the entire serial communication. Okay. And the other one is SBUF, that is a buffer register. Buffer is meant for storing. So whatever 8-bit data we are going to transmit or whatever 8-bit data we are going to receive, that is going to be stored in SBUF register. Right, so SBUF is for storage purpose, data storage, and SCON is for controlling the entire serial communication. Right, so let us see what is that. Now in case of SCON, the SFR address is 98 hex and we can set and clear 1 bit. So it is bit as well as byte accessible, addressable. Right, and what all controlling does SCON do? Look into whether the serial communication should be enabled or disabled, on and off of the serial communication, whether 8-bit data is to be transmitted or 9-bit data is to be transmitted. And if there is communication going on, in what mode is the serial communication? Like in case of timers, we had mode 0, mode 1, mode 2, mode 3, 13-bit timer, 16-bit timer counter. Similarly, we are going to have 4 different operating modes of serial communication. So we are going to see the control word in detail. So SCON is the only control word for serial communication. And see into that buffer register, it's meant for storing data. Internally, right, there are 2 SBUF registers. and the address, the SFR address of both the registers is 99 hex. So we are going to have two hardware registers inside. The name is SBUF. They are going to have the same address, but one SBUF register will be activated by the read control signal and another SBUF register will be activated by the write control signal. See why this is so? As I said, the transmission and the reception can happen at the same time. Is that okay? Now, whenever microcontroller is receiving data, when it is the data bits are coming on RxD. Correct? So microcontroller is receiving the data, mean it is reading, taking it in. So whatever arrives on RxD will be stored in one SBUF register. And which SBUF register? The one which is activated by the read control signal. Correct? So if microcontroller takes in any information, any data, mean that is a read operation. So RxD data will be saved in SBUF register, which is controlled by the read control signal. And whatever microcontroller wants to transmit, that data will be saved again in SBUF, but that SBUF will be activated with write control signal. So remember students, there are two duplication of SBUF registers internally, but user does not understand that. For user, it appears as if they are using only one SBUF. Internally, it is managed by the microcontroller, which SBUF is to be used. Okay, so user will have only one SFR address and only one SBUF register. Is that fine? But physically, internally, two SBUF registers are available. Okay, students. Now we will see that SCON register in detail. Yeah. So just take a look at this. This is the control word SCON register, which is 8-bit SFR. Okay. So SCON RI, right? I stands for interrupt, but that does not mean interrupt is going to be activated. But interrupt can be generated. So just let me read it first and then I'll explain. RI, receiver interrupt, right? TI, transmitter interrupt. RB8. So when I say it is an 8-bit data, we say it is 0 to 7. D0 to D7 are the 8 bits. If it is a 9th bit, then that is called the D8. So this is where receiver 9th bit, transmitter 9th bit, TB8. Then REN is receiver enable. And these are SM2, SM1, SM0 are the mode control bits of serial communication. Okay. So SCON is an 8-bit SFR register. Address is 98 hex. You can clear or set the bit as well as it is bit as well as byte addressable. Okay, SCON.0, SCON.1. Okay, now let us see one by one bit. SCON.0, that is RI. RI stands for receiver interrupt. If this bit is 1, it means the reception is completed. End of reception. So if RI is 1, mean the reception operation is completed. If the bit is 0, mean microcontroller is still receiving data. Okay. Whether microcontroller has finished the reception or not, the checking can be done in 2 ways. Okay. I can write an instruction to check the RI bit. Jump if RI bit is set. Jump if the RI bit is not set. JNB or JB. If I check whether the reception is completed or not with the help of instruction, that is called polling approach. Okay, microcontroller is continuously checking, is RI 1? Is RI 1? If RI is 1, mean the operation is done. If RI is 0, reception is yet to be completed, wait. So microcontroller keeps on waiting. So that is called polling approach. The other way to understand whether the reception is completed or not is to activate the interrupts. When we study interrupt, we will activate serial communication interrupt, and as soon as RI bit becomes 1, serial interrupt will be generated automatically. Right? So whether that particular operation is completed or not, whether microcontroller has completed that operation or not, the checking can be done in 2 ways, either using polling technique or using interrupt technique. Polling technique is checking with the help of instructions. Interrupt is activating that serial interrupt. Correct? In polling, microcontroller is continuously busy checking the operation. We cannot use microcontroller to do anything else. That happens in polling. Whereas in case of interrupts, we will do all the initializations, SCON, SBUF, everything. We will activate the interrupts, and microcontroller is now free to do some other operation. Serial communication will keep on happening at the back end, and microcontroller will do some other operation. That happens in interrupts. Okay, so with this RI flag, either can also be used to generate an interrupt. That is what I want to tell you all. Okay, so now whenever that reception is completed, that internal hardware circuitry will automatically set RI. Okay. Now similarly, TI is transmission interrupt. Right. So if TI bit is set, it means microcontroller has finished the transmission operation. You can make use of TI to generate an interrupt. Or, right, we can check with the help of instruction whether TI has set or not. TI set when transmission is completed. So that these are the 2 bits indicating the operations are over. Correct? Now the next. We will see different modes in serial communication. We can transmit 8-bit data as well as we can transmit 9-bit data. Right? Like what we saw in the frame format, which is the 9th bit, that parity bit is the 9th bit. Are you getting me? So if I do not have the parity bit in the UART frame, it means we are transmitting 8-bit data. If I'm adding the parity bit, it means now we are transmitting 9-bit data. The start and the stop bit, and what is that frame inside? It's of 9 bits. 8 are the data bits, 9th is the parity bit. So that 9th bit is placed in a SCON register. During reception, the 9th bit will arrive automatically on RB8. Right? So during reception, what did I say? The data bits are received serially and one by one are stored in SBUF. So 8 data bits will be available in SBUF register, and the 9th received bit will be available in SCON register RB8. Fine, students? Similarly, while transmitting 9 data bits, 8 data bits we will be storing in SBUF, and the 9th data bit to be transmitted will be storing in TB8. Right? So TB8, 9th data bit to be transmitted, RB8, 9th data bit to be received. SCON. Next, look at the 4th bit, REN, receiver enable. If this bit, we will be setting this. Logic 1, logic 0, programmer will be setting. So enable the reception. If REN is 1, reception is enabled. And what about transmission? When is transmission enabled? As soon as we store any data in SBUF register, automatically the transmission begins. But for reception, there is a bit to enable the reception, REN. Do you get me, students? Reception is enabled by this 4th bit on SCON. That 4th bit should be set. Whereas transmission, there is no such bit. But then how does transmission begin? As soon as some data with the help of instruction, if I load some data in SBUF register, automatically the transmission begins. Okay. Now the next, the fifth bit, SM2. This is for multi-processor communication. Now see here students, what does that mean? Now suppose I connect a memory, a serial interface memory with microcontroller. So in the entire interfacing, there is only one microcontroller, whereas the rest others are the peripherals. It can be memory, it can be ADC, it can be sensors. So in the entire system, there is only one microcontroller. Correct? Whereas in one system, I can have more than one microcontrollers. Correct? In some high-end systems, I can have multiple microcontrollers working together. That is called multi-processor system. In that case, the one who transmits is called as a master, and the other microcontrollers who receive the data are called as slaves. So whenever there is such master-slave configuration, multiple processors communicating with each other, right? We need this SM2 bit needs to be set. Okay. In more detail, I will explain about how that multiprocessor communication works. So for time being, what is SM2? When SM2 bit is set, it means multiprocessor communication is enabled. If SM2 bit is 0, there is single microcontroller in the system. Okay. And then SM0, SM1. Hope student. So we will look into SM0, SM1. SM0, SM1 are going to set the modes of serial communication. Right? Now let us see the different modes of serial communication. So see here, I have only mentioned SM0, SM1. 00 mode 0, 01 mode 1, 10 mode 2, and 11 mode 3. Okay. So 00, it means it is mode 0 serial communication. Okay. So just let me write there mode 0 serial communication. A minute. What is that? Mode 0 serial communication. Mode 0 serial communication. Now what is mode 0 serial communication? It is like a shift register serial communication, or it is synchronous serial communication. See here, even though we are saying what type of communication we have UART, universal asynchronous, but we can still have synchronous communication between the two devices if we keep microcontroller in mode 0. Okay, so mode 0, keep in mind, it's a synchronous serial communication. And at what frequency the communication happens? It is F oscillator divided by 12. So if it is 12 megahertz crystal oscillator, it means the synchronous serial communication happens at 1 megahertz. And that's the limitation. There cannot be any other frequency communication. The synchronous serial communication should happen at 1 megahertz compulsory. Is that okay? Now see, whenever we perform synchronous serial communication, right? See, there are two pins, TXD, RXD. So from microcontroller, it is communicating it with some other device. And if it is in mode 0, then data will be transmitted 1 bit at a time. In synchronous serial communication, data will be transmitted on RXD pin. See, there is some difference. Data transmission happens at RXD pin, and TXD, on TXD pin, 1 megahertz clock is sent. Are you all getting me? Up till now, what did I say? RXD receives the data. TXD, there is a data transmission. But this is applicable whenever it is universal asynchronous, UART communication. Asynchronous communication.
But whenever there is synchronous communication, mean in mode 0, data will be transmitted on RxD. That is transmission and reception. Both will happen on RxD. Whereas TXD, what is sent? 1 megahertz clock. Always. Keep this in mind, students. So that is mode 0. Okay? And we rarely use synchronous communication, as I told you all. Right? We always go for asynchronous. Okay? Next, mode 1. 01 is mode 1. Okay. Now mode 1 is 8-bit universal asynchronous reception and transmission. And the frequency at what rate the transmission should happen is variable. We can select the desired frequency, and that is what we call it as baud rate. Okay. In synchronous communication, the baud rate is fixed, F oscillator divided by 12. Whereas in mode 1, asynchronous communication, 8-bit data communication, and we can have a variable baud rate. At different frequencies, the communication can take place. Remember this, baud rate is variable. Next, 10, that is mode 2, 9-bit data communication. So 8 data bits and the 9th bit is the parity. So 9-bit data communication, asynchronous communication, and there are only 2 baud rates, F oscillator divided by 12 and F oscillator divided by 32. Oscillator is that crystal oscillator. So whatever oscillator you connect, that frequency gets divided by 12, and at that baud rate, the communication takes place. So there are only 2 baud rates available in mode 2. Asynchronous communication, 9-bit communication with 2 baud rates. Okay. And mode 3, it's again asynchronous communication, 9-bit data transfer and a variable baud rate. The programmer can decide what is a rate of transmission. So these are the 4 operating modes of serial communication. Mode 0, synchronous serial communication. Mode 1, 2, 3, asynchronous. Mode 1, 8-bit asynchronous, variable baud rate. Mode 2, 9-bit asynchronous, 2 fixed baud rates. And mode 3, 9-bit asynchronous, variable baud rates. Hope you all are understanding these, students. Now see what that SBUF register I have shown here. You can always, this is not bit accessible. Either you will be reading or storing 8-bit data, and the SFR address is 99. So either refer it by name SBUF or you refer it by its address. Okay. So for user it appears there is only one SBUF, but internally there are 2 SBUF registers, one for transmission, another for reception. Okay. And then I said, see, variable baud rate. Where is that variable baud rate? In mode 1 and in mode 3. We have variable baud rate, that is user can fix up the baud rate. And this is the equation for deciding the baud rate. Look here, students. And baud rate is how many bits are sent in 1 second. That is called baud rate. So the most widely used baud rate is 9600, 9600. Okay. So the baud rate 9600 multiply by 2, that's a higher baud rate. Divide by 2, you get the lower baud rate. Divide by 2, then it is 4800 baud rate. Again divided by 2, 2400 baud rate, and so on. There are various baud rates available for serial communication. Most frequently used is 9600 baud rate. And what is a baud rate? How many bits are sent in 1 second? That is the baud rate. Okay. Now see here, students, when we say we are having 8-bit data, right? We are going to store that 8-bit data in SBUF register. Whereas the frame formation is done automatically internally by the microcontroller. That is, putting the stop bit and putting the start bit happens inside automatically. What the programmer has to do? It has to only give the 8-bit data and store that data in the SBUF register. The frame formation happens internally. We need not worry about the start and the stop bit. Right? So while transmitting, the frame is automatically prepared by the microcontroller, and at the reception, that start and the stop bits are automatically removed by the microcontroller inside. And what is available to the programmer? That extracted 8 bits. Where do we get that 8 bits? In the SBUF register. So we need not worry about preparing the frame. The frame is created internally automatically. We just need to give 8 data bits or the 9 data bits. Okay. So the equation for baud rate is here 2 raised to S mod. And where is this S mod bit? This S mod bit is available in PCON register, power control register. So this is related to serial communication, S mod. We will see what this S mod is. But let us look at the formula once. 2 raised to S mod. So either that S mod bit is logic 1, logic 0. Mean it will be either 2 raised to 0 or it will be 2 raised to 1 into the oscillator frequency, crystal oscillator, whatever you connect, divided by 32 into 12 into 256 minus TH1. Now what is this? If you hear those timer lectures, 256 minus TH1, it's indirectly indicating we are using timer 1, TH1 is timer 1, and the count is 256, mean it is mode 2. It means to generate the baud rate for serial communication, we will be using timer 1 in mode 2, auto reload mode. Are you getting me? Okay, so that is the equation, right? So if the baud rate is known to me, 9600 baud rate, the S mod bit is by default 0. Okay, so it is 2 raised to 0, oscillator 11.0592, right? In serial communication, we will be taking the exact frequency 11.0592. We will not round it up. If we round it up, the calculation will come in fractions and the baud rate changes. So it is very sensitive. Okay, so the oscillator should always be 11.0592 megahertz. Okay, and with all these known parameters, I will find out what is the count to be loaded in TH1 register. If I load that count, I'll be getting the desired baud rate. I'll be getting the desired square wave. Okay, students. Okay. I stop here for today, students.